Okay, so picking up where we left off last time, new section. We're going into section 6.3 now. It's about something called conservative vector fields. That's I suppose, technically true. It's really not the focus of this section, and depending on how you look at it, of course. But first, real quick, what is a conservative vector field? It's just a vector field that's a gradient. And, of course, when it comes to terminology, I like terminology that's as on the nose, as directly communicative as possible, and I feel like gradient is already a pretty good word describing a vector field that's a gradient. Anyway, be prepared, mostly with physics motivations, you will see this word conservative around, right? And there's good physics reasons for it, I suppose, but I'm going to just call them gradients. Okay, so here we go, big theorem, fundamental theorem of line integrals. Fundamental theorem of line integrals says that if you have a vector field that is a gradient, and you want to compute a vector line integral of that vector field, then here you go, nice, handy, convenient little formula, f of b minus f of a. Note how much this looks like the fundamental theorem of calculus, doesn't it? Right? It's practically a copy, in some sense, of the fundamental theorem of calculus. It's not a coincidence. Ultimately, the fundamental theorem of calculus and the fundamental theorem of line integrals come from the same thing, really. Note as well that there is the asterisk, that this is not just any old random vector field off the street. This is specifically, whatever you're doing a line integral of, that vector field has to be a gradient. Right? And in particular, notice that the anti-gradient, you have to know what that anti-gradient is, because after all, that's what you're going to be plugging the endpoints into. So just like the fundamental theorem of calculus. All right, now let's talk about where this comes from, and there's different points of view that you can take. Y'all probably can guess I'm going to take an accumulation and density point of view, because I like how all of the theorems that we're talking about, all of these sort of analogous theorems, they can all be understood from the same point of view, which I think is nice, kind of unifying. So here we go. In this theorem, there is an accumulating quantity, again, change, just like with the fundamental theorem of calculus. Right? So what do I mean by change here? What I mean is change accumulates over curves. So if you have, for example, a curve like this, right? Well, there's a certain amount of change that happens to whatever function little f you're talking about. From this starting point to that ending point, the function changes by some amount. Then if you ask, related, okay, well, yeah, but how much is the change that happened over this first portion of the curve? And how much happened over this second portion of the curve? And then you ask specifically the accumulation question. Is the purple change equal to the sum of the green change and the blue change? And, well, yeah, of course it is. Right? It's just sort of an immediately relatable claim. I like to think in terms of how altitude changes. Right? So let's suppose that this is not just some random curve. Let's suppose this is a road, some sort of a winding mountain road, and you're keeping track of altitude as you drive along the road. Well, how much altitude you gain on the green portion? How much altitude you gain on the blue portion? Those have to add up to how much altitude you gained over the entire purple curve. Pretty believable. If you want to see the algebra of it, that's what this is right here, right? But I think it's pretty immediately relatable. Okay. All right. Okay, so we have an accumulating quantity. Next question, what's the associated density? So what is the relationship between how much I displace along a curve and then how much of this accumulating quantity called change that I get as a result? So I'm going to remind you all of this formula right here from Chapter 2. This goes pretty far back. Right? But if you have an input displacement, and you want to know how much is the output change that corresponds to that input displacement, well, dot product with the gradient does it. Okay? Now, of course, we can rewrite the dx vector as TDS, And having rewritten dx as TDS, now I'm going to take a sort of a different point of view on what I had circled in blue. Let me sort of redo this like this. And now notice, just as we would like, we have accumulating quantity as this expression times what you might call size in the domain, namely how much distance did I make? How big is that little piece of curve? And being a curve, of course, what that means is how long is that little piece of curve. So what we have in purple there is pretty straight interpretation, our density. That's how much of the accumulating quantity per unit size. So let's see here. Yeah, so the density is gradient dot t. So we've seen, I'm going to come back and talk about this oriented density in just a second. For the moment, though, let me come on back down here. And we've seen how to put together accumulation theorems once we have these pieces ready to be put together. We made the observation first that change is an accumulating quantity. There you go. The whole is the sum of the parts. That's what it means for change to be an accumulating quantity. Second, how much is this little bit of change? Well, as we just discussed, gradient dot t times ds. Right? And all together then we have ourselves our theorem. By the way, this is our first version of the fundamental theorem of line integrals. You'll notice now, real quick, this TDS is, of course, dx. So what I have circled in green here, it's using sort of the alternative notation for vector line integrals, but f of b minus f of a is the vector line integral of that gradient. Everybody happy? Okay. All right. So now I am personally going to not prefer to write it that way. Here's how I kind of prefer to write the fundamental theorem of line integrals. I like to see vector line integrals like this, right? Because ultimately the integrand then is what looks like the integrand, right? And the differential telling your movement along the curve, well, that's what this dx is. So more natural, I believe, notation. So if we're going to say that gradient dot t is the actual density of change, that's how much of the actual, accumulating quantity per unit size. What then interpretation would I make of the gradient by itself? Right? This is something we'd like to have a sense for, because after all, it is really the integrand, right? So let's come back up here for a moment to remind ourselves. We have this formula here. But where did it come from? Right? It actually came from this formula right here. Now, we didn't stop with this at our first pass through this, because this isn't really size. Right? This is size over here, and I had to kind of separate out the capital T vector. Fine. But here's the thing. dx does tell you, among other things, the size. Right? It tells you size and direction. Orientation, we call it sometimes. So, a pretty reasonable point of view is to say, all right, well, look, I got my colors crossed here. This dx vector, it's not a scalar notion of size, but it's a vector that's telling you about size. So, I'm going to call this oriented size. You could call it vector size, I suppose. Right? I like the idea of oriented. It's just aesthetics. So, with that in mind, what we have encircled in red here, this is a relationship between accumulating quantity and not scalar size, but oriented size, and a relationship between quantity and oriented size. Wouldn't it be reasonable to call that then an oriented density? Now, this is just a point of view. Question comes up of what's this worth, right? Why should we care about this? It's going to turn out to be a pretty handy idea later on. Right now, I just kind of want to plant the thought in your minds that you can, again, kind of broaden your idea of what a density is. But we spent a bunch of time talking about how, hey, it doesn't have to be, the quantity in question doesn't have to be mass. It can be any accumulating quantity. And we spent some time talking about how the size doesn't have to be volume. It could be volume or area or length or whatever is appropriate. And now I'm just saying let's broaden it a little bit more. Not only could it be various different scalar quantities, we could kind of sort of make it work with it being a vector quantity as well. Okay. All right. So with this in mind, with the gradient being our oriented notion of density, then here we go. That's how you make sense of the integrand down here. It's oriented change density. Let's see if I can fit that all. There we go. Change density because that's the accumulating quantity. Oriented because it's a vector. Okay, like I say, it's just a point of view. Okay, let's do one. Let's get our hands dirty. Here we go. We have a vector field. We have a curve already parameterized for us. And the question is to compute a vector line integral. Okay. Now, actually, before I go on, let's look at the statement of the question here again. Where's the tip that we should solve this problem by one method versus another? And not only is there not really a particularly good one here, there's actually even sort of a misdirect in the way this question is phrased. And I don't do this because I enjoy being mean to students, right? I do this because this is how life's going to come at you, right? And I want you to be prepared for what you're going to see in real context, right? Sometimes what you know about your domain won't be exactly what you most conveniently need to deal with it, right? Sometimes it'll even maybe make it look like you ought to go down one road when really you ought to go down another. So in particular, here this curve is given parameterized, kind of makes it look like we should pull back through the parameterization. Don't fall for it, right? Make your own decisions. Don't let arbitrary, meaningless things like how something comes at you make your decisions about how you solve the problem. Right? So just be on the lookout for that kind of thing. So this observed, we're going to use the fundamental theorem of line integrals here. We, after all, are being asked to compute a line integral. I'm going to notice that our vector field is a gradient. Easily checked. Right? Take this function x squared y squared, compute its gradient, right? X partial, y partial works. So this is not just a random vector line integral. This is a vector line integral of a gradient. This is exactly what our fundamental theorem of line integrals is all about. Right? And so all we have to do is identify what is our anti-gradient. After all, that's what we're going to be plugging A and B into. Oh, lucky break, our anti-gradient we already see. There it is. There's our anti-gradient. That's what is the function that we're going to be plugging our endpoints into. Yep?
Isn't the anti-gradient not unique though?
Oh, yeah, that's right. It's not unique, but any anti-gradient will give you the same answer. Yeah, so it's kind of like with the fundamental theorem of calculus, right? You can always say plus C in the fundamental theorem of calculus. Likewise here. And it doesn't matter what C you pick. That C will kind of cancel in the subtraction here. Is that satisfying? Everybody good? Okay. All right. So, so all we got to do now is figure out the A and the B and plug and chug. Where does this curve start? Let's see here. This curve, where does it start? Well, it starts where t is equal to 0. What point is that? Well, plug in that value of t. See what you get. There's your starting point. There's your A. Where does this curve end? Well, apparently it ends when t gets to pi. Okay, well, so again, we're going to plug that in. That gives you this point. This is your b. Everybody happy with that? So it turns out that all we actually used the parameterization for here was not much. It was just to infer from the starting and ending values of t what are the starting and ending points on the curve. That's all we need the parameterization for. So again, don't fall for all this information being given and feel like you have to figure out how to follow that specifically. Much easier solution here using the fundamental theorem. All right. Real quick, I'll point out we could have actually done this pulling back through the parameterization. After all, I've got an x and a y. I could just kind of plug and chug, right? Just keep in mind what's going to happen there. X and y are each one of them is trig. That means there's going to be a significant amount of trig in your vector field. Your dx has an x prime in it, which is going to have again, a little bit more trig. So this actual, when you write this down as a t integral, it's going to have a lot of trig in it, and you may or may not actually want to do all that trig and remember those half-angle formulas and deal with the various constants and stuff like that, right? So I think this is a much better solution. Yeah?
Sorry, could you just explain one more time how you're using, finding the anti-gradient in this case?
Yeah, okay, so yes, I deliberately swept that under the rug and you caught me. So yeah, there's a big question here. I pulled this out of thin air, right? I conjured it, right? Now, in fact, when I wrote this, I actually dreamed this up first and then took the gradient and then made it look like that was where I started, which I didn't, right? Okay, so there is a method, and so, significant question, how are you supposed to find your anti-gradients? Are you supposed to just consult your inner oracle and just see it, right? Or is there a process? There's totally a process. We'll get to that later. It's a bit of a distraction from a bunch of ideas I want to develop now, but it's a very reasonable question, and we'll get to it probably on Wednesday.
So how does that impact, what are we plugging in for, the little f of a and b? Are we using that?
Yeah, so this is the f right here.
Okay.
This is your little f.
Okay.
Right? That is what goes there. And then the a and the b are the points that you plug into it. Yes.
Thank you.
Yeah. Okay. Right. Okay, here's another idea. The book actually starts with this idea. There are kind of always pros and cons about different paths that you can take through a bunch of ideas. I like to start with the fundamental theorem myself. This idea of path independence is a weird one. It's an outrageous suggestion that doesn't seem like it ought to be possible. I'm going to start with what I think is a pretty uncontroversial, pretty believable statement. If you're interested in a vector line integral, well, it depends on your curve, doesn't it? I mean, after all, these are the points that you're going to be plugging in and seeing what the vector field is at these points, right? That's the domain. That's where you're evaluating stuff. If you pick a different curve, you're going to be plugging in totally different points. Of course you would assume you're going to get a different answer for the value of the line integral. I don't know, I just feel like that's just should be clear. So with that in mind, let's look at this seemingly outrageous suggestion down here that they claim that there exist vector fields that are what we call path independent. The book says it has path independent line integrals. To me, that's too many syllables. I think it's easier to say path independent. Anyway, the idea is that this vector field, that there might exist, I'll say, some vector field such that any two curves asterisk, a little micro asterisk here. They do have to start at the same point and they have to end at the same point. But that's just 2 points. There's a curve with infinitely many points on there, right? The idea is that any two curves, starting and ending the same points, any two curves should give you the same value of the line integral, but they're totally different curves. Again, it doesn't seem like that's how it ought to work. It seems like this should be basically impossible. Okay. Now, in support of my suggestion, and I do this for dramatic purposes, of what an outrageous proposal this definition is, let's look at I think a pretty obvious, believable counterexample. Here's a vector field. I've got a picture of drawn here. The field vectors get longer. The more you go to the right, all of the field vectors point up. Easy to persuade yourself that's what that vector field looks like. Let's look along a couple of different paths. Right? Here's a first path. Here's a second path. They start at the same point as required. They end at the same point as required. And if you just kind of take an explicit look, I mean, along in here, the vector field itself is 0. There's no line integral being accumulated there. And if you look along in here, the field is pointing up. The dx vectors are pointing to the right. That's perpendicular. No dot product there. So our green line integral should be 0. I didn't even have to do any calculations. Right? That's just using sort of little geometry freebies. And then now let's do the same thing down here on the blue curve. Well, again, orthogonal down here. So no integral on that portion. And then along this portion, the vector field is positive and upward. The dx vectors are also exactly the same, positive and upward. That dot product is going to be positive, non-zero and positive. So along in here, pretty clearly positive. And so with that in mind, this blue line integral sort of obviously not 0. And all of this is as expected. I mean, for crying out loud, I mean, this is what an easy, unremarkable vector field, and it behaves exactly as we would expect. Why would you think that any two vector line integrals on totally different curves should be equal to each other? Outrageous, right? Drama over. Here's how it works. Here's why it's not that outrageous of a suggestion. In fact, not only does there exist a path-independent vector field, but there's a bunch of them. And it's not even hard to find them. In fact, every gradient is path-independent. Not hard to show. Here we go. Let me show you how this works. Here's a common starting point, common ending point, curve 1, curve 2. Right, we're going to compare the integral on curve 1 with the integral on curve 2. Don't really particularly expect these to be the same, but here's the thing. Conveniently, because the vector field is a gradient, right? Because the vector field is a gradient, I can use the fundamental theorem of line integrals. Fundamental theorem of line integrals says either one of these integrals you want to compute. Let's take the green one just to start. This is not just a random line integral. This is a line integral of a gradient. And the line integral of a gradient can be computed by looking at the endpoints. F of b minus f of a. Ditto for the blue one. Still a line integral of a gradient. Still can be computed by looking at the endpoints, f of b minus f of a. And these two curves have the same starting point and same ending point, and therefore these two integrals are both equal to the same thing, and therefore they're equal to each other. How about that? Isn't that wild? So, I think it's really interesting how this works out, that not only is path independence possible, it's actually pretty common to happen. All gradients are path independent. I have to constantly put asterisks at point. Yeah, I don't want to get bogged down in regularity issues. That's not really what this class is about. Continuity is a sticky wicket on this. We do have to actually say continuous. Not anything we're going to need to worry about. Okay. Now, harder to show but certainly still true, and also not not unrealistic. And you could do this if you want, but you don't have to. Not only is every gradient path independent, but every path independent is also a gradient. So this goes both ways, again, in the category of looking only at continuous vector fields. Path independent and gradient are simultaneous. They're two different features, you might say, of the exact same special vector fields. Okay. Everybody okay? All right. Here's a different way to say it. Now, why do I want a different way to say it? It turns out that there's some situations where this is convenient. So again, just a setup, common starting point, common ending point. One curve going one way, the other curve going a completely different way, getting to the same ending point. And path independence says that these two line integrals are the same. Right? So this is what path independence says. Green equals blue. Well, I could rewrite that as green minus blue equals 0, right? I mean, nothing happened there. That's the same statement. Okay, but now let me take a look at this difference, green minus blue, and keep in mind that a minus sign amounts to going backwards on a curve, right? So I have a plus sign as I go around C1, then a minus sign as I go around C2. I claim that this suggests that I'm going around a new curve that is forward along C1 followed by backwards along C2, which frankly is pretty easy to draw. Here we go. I start there, I go forwards along C1, and then I just go backwards along C2. So again, I don't really do anything yet, but an alternative formulation of green equals blue is orange equals 0. That's a different way to think about it. So let me say that in words instead of colors. What we call path independence, this idea of you always get the same vector line integral as long as the starting and ending points are the same. This idea of path independence is equivalent then to this other point of view that says as long as all of these orange curves, as long as all closed curves, right? So notice that this orange curve here starts here, goes around, ends also here, right? As long as on all closed curves, this orange line integral is equal to 0. Same thing. Everybody on board? By the way, reminder, a closed curve, and you compute a vector line integral, remember we have a special word for this. This is circulation. So another way to say that a vector field is path independent is that all circulations are 0. Okay, so here's a fun example. I'm going to consider a particular vector field, namely what I like to call the steepness vector field, namely the gradient of h being the altitude function. You remember I like to think of altitude as being a function of x and y, right? Function of longitude and latitude, if you like. Okay, so what can we say about this vector field and why would I call it steepness? Well, the gradient points uphill, and the magnitude tells you literally how steep is it, right? So pretty reasonable, I think, to call this the steepness vector field. Anyway, point being, it's clearly a gradient, kind of by definition. As we just discussed, gradients are path independent. We just came up with a new formulation of path independence. Path independence can be phrased as all closed. Note the little circle here. This little circle in the integral symbol is just a shorthand for a closed line vector line integral around a closed curve. So closed vector line integral equals 0. Circulation equals 0. Okay, what does this tell us? Let's look inside of here. What is this f dot dx? Well, let's see here. F is the gradient of the altitude function. Dx is my input displacement. Gradient dot displacement gives you change. And again, specifically of h being the altitude function. So this little green summand that I have here that we're adding up along this entire curve, this is just telling you how much your altitude changes. And so the integral is going to tell you your total altitude change on your closed curve. So what we have here is a statement that if you're looking at the steepness vector field, if you're keeping track of how much your altitude changes as you go around a closed curve, grand total around any closed curve, your total altitude change has to be 0. Now let's talk for a moment about how plausible that is. If I go for a walk around campus, my altitude goes up and down, right? A little bit of a hilly campus here and there. But when I come back to exactly where I started, I mean, my grand total altitude change is 0, right? I mean, I'm literally back where I started. Is that satisfying? I mean, I'm going to say this is a calculus version of a statement that should be intuitively kind of immediate, right? Okay. So, nevertheless, it is a calculus statement about what in this drawing here is presented as being possible when in fact it isn't. So I don't know if y'all are familiar with the artist named M.C. Escher. Bunch of sort of geometric impossibilities and drawing illusions of various sorts. Very clever, very creative, a lot of fun. So let's talk about the Escher stairs that we have here, and let's think about these people sort of on the outside here of the stairs, and notice they're all walking up those stairs, and then they continue walking up the stairs over there, and then they keep walking, and they're going up these stairs, and then finally they finish by going up those stairs, right? So this is obviously an illusion. This is not physically possible. But it would appear, Escher is suggesting that this line integral is non-zero. He's suggesting that these people walking around the outside are gaining altitude as they walk around this closed loop. And what we have here is the calculus refutation that, that's nonsense. Not possible. Grand total's got to be 0. Does that make sense to everybody? All right. Okay. Oops. Okay. Now, who cares? Always a good question to be asking. How does this improve my life, right? To understand this idea of path independence. I claim that it's actually very useful conceptually in certain kinds of applications, and in particular physics. If you want to make sense out of the idea of potential energy, there's some sticky questions there. Right? Now it's tempting to say, all right, well look, when you oppose a force, so here I've got my stylus in my hand, right? And if I lift, right, I'm performing work, and I therefore the amount of potential energy in the pencil, whatever, is lower here, and then higher potential energy here because I've done work to get it into there, right? But I don't know if you've ever thought about this before. Notice how there's no such thing as friction potential energy, right? If I, have this chair here, right? I perform work when I've got to exert some force to get it to move against friction along the floor. Does it somehow have more potential energy over there than it does over here? No, not at all. Not even a little bit. So how come gravity gets to have a notion of potential energy, but friction doesn't? Right? So, and what about other forces? What about electric force? Does the electric force get to that one? What about the magnetic forces? Which ones get a potential energy and which ones don't? It's a pretty deep question. And I'm going to say that one of the big ideas that helps you distinguish and decide in which of these contexts does the notion of potential energy even make sense, path independence, deep down, is what really makes the most sense of arbitrating these questions. So very useful as a conceptual tool, independent of an actual computation. It's not necessarily always about computations, right? So very useful conceptually. A little bit of use computationally, but I want to point out why we are kind of less interested in path independence as a computational tool, because if you think about it, if you're even allowed to use path independence, that means that it's a gradient, which means it has an anti-gradient, which means you can use the fundamental theorem of line integrals, which frankly is pretty awesome. So who needs path independence if you've got the fundamental theorem of line integrals? Know what I mean? So, I guess that's kind of true. But I will point out that in this strategy here, there is a potentially sticky wicket that I kind of glossed over, and that is you are going to have to find that anti-gradient, as you pointed out, that I kind of swept under the rug previously, right? So what if the vector field is a gradient, but you don't know how to find the anti-gradient? And that happens sometimes. Right? So let me show you how to deal with that circumstance. Path independence is a lovely tool. Here's the scenario. I'm going to take it as a given. We'll clean this up later, but I'm going to take it as a given that this vector field is path independent. Again, I'll show you how to determine that for yourselves in a few minutes. Path independent, cool. And that being said, we're going to look at this path, top half of the unit circle going clockwise like so. There's my path. I got a vector field and a path. Let's compute that vector line integral. And I, again, suppose you could parameterize this, but again with the sines and the cosines, and again with there's going to be some significant trig half-angle formulas and stuff, right? And so it doesn't look like something we'd particularly want to do. Okay, so here's where we're going to use the path independence, right? It's given that this vector field is path independent. That means that as long as I tie down the starting point, as long as I tie down the ending point, not allowed to move those. But that said, you can pick any other path you want that starts and ends at those same points. Right? I could do that one. Go crazy, right? You have endless choices of curves. Now, which one are you actually going to pick? Obviously, you're not going to do any weird loop-de-loops. Obviously, you're going to try to make your life as simple as possible. We're going to choose a straight line. Right? So now, where do I come up with this outrageous suggestion that I'm just going to throw away the curve that was given to me in the statement of the question and just pick arbitrarily, selfishly, a brand new curve? What gives me the right to do that? Path independence. Right? So if you know that your vector field is path independence, that gives you pretty tremendous rights there. And now that I have my new curve picked, I'm going to just totally erase that green curve. I don't care about it anymore. I don't need it at all. And this new curve is really easy to parameterize. It's a straight line. Notice, very importantly, no trig. Pretty sweet, right? And the calculation goes through really nice. In fact, it's even easier than no trig. In fact, it's basically a freebie. So a couple things you're going to notice about this parameterization that we have here, or more to the point, this curve that I have here. Notice immediately, I don't even really need a parameterization, but it's just perfectly obvious from the picture that y is 0 on this whole blue curve. It's just along the x-axis. Y is always 0. And that means that I get a 0 here. Now, this is an easy observation. Next thing to observe, let's see here. I will use the pencil here. Anywhere I am moving along this curve, there's going to be little dx vectors. Right? Don't forget the dx vector has coordinates that you can write as dx, dy. And now again, picture appeal. Looking at the picture here, notice my dx vector is horizontal. Perfectly horizontal. There's no up. There's no down. Perfectly horizontal, which immediately tells me that this dy, 0. Right? And so I have a 0 there. And so as I'm doing this integral, not only do I not have to deal with trig, I don't have to deal with anything. The dot product is immediately 0, game over, we walk away. Isn't that nice? All right. So can be a neat computational tool. By the way, in general, I think it's a good idea to be on the lookout for wonderful little opportunities like this. This first observation in orange, if you will, that y is always 0, kind of thing comes up a lot. So heads up on your domain, and keep in mind your domain is free information about the points that you're plugging in. And if you have beautiful free information like y is always 0, stick it in there. Very helpful. Okay. All righty. Okay, now, to be fair, this question I could have done a different way, right? In fact, without too much trouble, I can kind of clever, smart alecky, thinking it through. I can come up with an anti-gradient. It's not that hard to persuade you. Just play the game, just kind of think about it. But not every question will be kind of a nice little freebie like this where you can kind of just write one down. So in this case, yes, I could have found an anti-gradient. I could have used the fundamental theorem of line integrals. That would be a distraction from the point of this example. The point of this example is to see how to do it the other way. Okay. And in plenty of circumstances, it will not be that easy. Okay. Local test. So, how do we know? How do I know if a vector field is a gradient? Or said differently, how do I know if a vector field's path independent? We already know these are the same. We already know that any gradient's path independent and vice versa. But given a vector field, how do I know if it's one of these cool ones or if it's not? So, theorem, right? Neat theorem here. The theorem says that what you have to do, what you can do, is just look at Green's operator, and if Green's operator is 0, then you're good, right? If Green's operator is 0 everywhere, that is indeed a gradient. It is indeed path independent, and go ahead and play path independence games, and it's all fine. Pretty neat theorem. I call this a local test. I think that's a nice terminology because if you look at how this test works by simply computing Green's operator, and Green's operator is a formula that I can plug points into. Any point. I don't need to look at all points at the same time. I can just plug in one point at a time, and it's a relatively easy test. This formula is either 0 at every point, or there's some point where it's not 0. And again, you really only have to look at one point at a time. And I'm going to distinguish that from, by contrast, the harder question of, how would I decide if there's an anti-gradient? Well, very importantly, it's not good enough for me to find a function whose gradient happens to be coincidentally the same as that of the vector field at just one point at a time. Nowhere near good enough. I need to find a single function whose gradient equals f simultaneously at all points with just the one function. So this is what I would call not a local problem. This is a harder sort of global problem. Anyway, that's just terminology. Why does this work? Well, as previously discussed, gradients are all path independent and vice versa. And don't forget, here's our alternative phrasing of path independence. Path independence would be phrased as all circulations, closed vector line integrals, all circulations are zero. Okay. So we already know these three green conditions are all the same. All right. Let's talk about now Green's theorem. Green's theorem says that these closed vector line integrals are all double integrals of Green's operator. Let me get rid of the distraction there. There we go. Green's theorem says closed vector line integrals, circulations, are all double integrals of Green's operator. So, if we're talking about a vector field where the circulations are all zero, another way to say that then is that all of these double integrals of Green's operator are all zero. And now I want to look at this statement here in blue. How could that be? This has got to be for every domain. Just like this has got to be for all closed curves. This claim that this double integral is zero, this has got to be zero for every domain in R2. And how's that possible? Surely, I mean, if you have some function, whatever this integrand is, Green's operator, right? Whatever that is, it seems like there should be some domain somewhere where this integral is non-zero. Just kind of look for where this orange function has a kind of a bump or something, where it's kind of, and just pick a small domain right under the bump, and it seems like you'd have a positive integral there, right? How could it be that they're all zero? There's really only one possible way, and that is if this integrand is itself always zero. So that's the idea. That's the big connection. And I like to separate this into three, or excuse me, kind of, depending on how you look at it. Let's say two groups of observations. These green observations are just observations about path independence. The equivalents of these two blue statements are, this is just kind of a statement about double integrals and how double integrals work. And the thing that connects them, right? The thing that connects them is Green's theorem. So Green's theorem does the heavy lifting in making sense out of this test. How are we doing? Is everybody on board? All right. Okay, here's a different way to think about it. Something a little bit more intuitive, perhaps. I mean, anyway. Basically, if you think about what does it mean to have a gradient, right? Namely a path-independent vector field. Well, one of the big ideas, as we discussed, if you're doing a line integral of a gradient, all your circulations have to be zero. If you're keeping track of a gradient as you move around a closed loop, f of b minus f of a, and the starting and ending point being the same, these circulations have to be zero, and I'm going to say sort of from the point of view of keeping track of how the function's changing as you move around the curve. Right? What is this statement here saying? This is saying circulation density is zero. And if you think about it, circulation density being zero, arguably, is also saying that circulation is zero. This is saying circulation is zero by thinking about how that adds up over the interior. Whereas what I have in green over here is thinking about how circulations have to be zero because of how they add up around the boundary. So that's, like I say, two different ways of thinking about it. That, these two statements are equivalent because in their own different ways, they're both just saying circulations are all zero. Okay, so you might like that point of view better. Okay. Real quick, terminology, a little bit of terminology. This feature, Green's operator being zero, is described sometimes as irrotational. Vector field is irrotational. I think the language on this kind of actually makes pretty good sense. If you think about it, Green's operator is telling you about how the fluid is or isn't rotating. And so if it's equal to 0, wouldn't irrotational just kind of make sense? So this is another example of terminology that I think is fantastic, right? It's just spot on. It's getting right to the point. Not any rotational aspect. It's right on. Okay. All right, and we appear to be out of time. So I'm going to draw the line right here. We'll pick up here on Wednesday. Y'all have a good day. See you later.